8 patients with depression were recruited to participate in a study for a new drug. The patients were randomly assigned to receive the new drug or a placebo, and they wouldn't know if they had received the new drug or the placebo. They would be blinded to this. After 1 week, their depression was assessed. Next, the patients were assigned to receive the new drug if they had the placebo during the first week, or the placebo if they had the new drug during the first week. So whatever drug they didn't have during the first week, they were then given that drug. After 1 week, their depression was assessed. So below is a table of the results. So here's patient 1. We don't know which drug they had first, but it was randomly, randomly assigned the first drug, and then during the second week they were assigned whatever drug they didn't have during the first week. So each patient would have received the placebo during 1 week and then the active drug during the other week. So here we see patient 1, their depression rating was 10.5 on the active drug and then 12.0 on the placebo. Now, 10 means, or lower numbers mean that they were closer to being very depressed, and higher numbers mean that you're happier. So for this particular patient, they have very low scores both during the active drug and the placebo, but actually during the placebo they were slightly happier. Okay, and we need to be careful here to recognize that because this is one patient who's receiving both the active and the placebo, we have to use paired design sort of analysis. We can't use the, for example, we can't use the independent t-test, two-sample t-test, okay? Because in order to use the two-sample t-test, the observations in each of the groups would have to be independent of each other. In this case, the observations in both these groups are actually tied by the fact that they're coming from a single person. Okay, so now that we understand the situation of which this data were collected, let's go on to answering Part A. Part A says, assume that the depression rate responses are normally distributed. Okay, so the fact that the depression rate responses are normally distributed, that'll tell us that we can go ahead and use a t-test, okay, or a paired t-test. And so it asks us to test if the average response or average depression rating is higher when taking the active drug than when taking the placebo. Okay, so remember that a high rating indicates that you're less depressed. Okay, so high rating is you're more happy. So we would ideally like to see that the active drug is reducing depression, right? So that would mean that you would have a higher score here under the active drug than you had while taking the placebo. Okay, so first step in doing all hypothesis testing is to define what your null and alternative hypothesis are. So in this case, our null hypothesis, or HO, is the mean, the average, mean or average, depression rating is not affected by the active drug. Okay, so that means that, remember, the null hypothesis is always the nothing happened hypothesis. And then your alternative hypothesis is whatever it is that you would like to see. We would like to see that the average depression rating is higher when taking the active drug than when taking the placebo. Okay, so the alternative hypothesis would be the average depression rating is higher when taking the active drug than when taking the placebo. So you could write this with symbols as well. Okay, so if we had used symbols to have written this, we would write mu1, that's the average. We would have to define that mu1 equals the average rating for the active drug equals mu2. So we would have to define the active drug as group 1 and the placebo as group 2. Okay, and then the alternative would be that mu1 is greater than mu2. Okay, that the rating gets higher when you're on the active drug than when you were on the placebo. Okay, so that's the null hypothesis, and that is the alternative. Okay, so the next step in the testing procedure is to calculate the test statistic. So the test statistic for a paired sample t-test is d bar. Okay, so d bar is the average of the differences. Okay, so you calculate the difference between each group, and then you calculate the average of those differences. That's what d bar is, divided by the standard error of d bar. Okay, so first thing we need to do is calculate what is d bar. And before you can do that, you have to calculate all the d's, all the differences. So you paste that here. I've calculated all the differences. So for example, this first difference is 10.5 minus 12.0. That's negative 1.5. 50.1 minus 55.0. That's negative 4.9. So forth. Okay, so you calculate the average of all of those differences, and that's what d bar is. So d bar equals 3.5. If you were to calculate all those, if you were to average up all these differences, that's what you'll get, 3.5. Next, we need to calculate the standard deviation. So recall the definition of how to calculate standard deviation. That will be 1 over n minus 1, the summation of all the data, okay, in this case it's a bunch of d's, di, minus d bar squared. Okay, so you sum that over all I equals 1, in this case 2. 8, in this case n is equal to 8, so that could have been 8 minus 1. Okay, so if you calculate this, what you'll get is 7.1598. Okay, so I recommend that you practice that. Go ahead, so each of these differences minus the mean, square it, sum it up, and then divide that by 7. And what you'll get is 7.589. Okay, so then once we have the standard deviation, we can then go on to calculating what's the standard error of d bar. Okay, so standard error, it's always standard deviation divided by square root of n. So that's what it is here, square root of n. N in this situation, it's not 16. Technically, we have 16 observations, right? But that's not what n is. N is just the number of pairs. Okay, so sometimes people will write n as nd, the number of differences, or the number of pairs. That will be the same thing. So if you take 7.1598 divided by the square root of 8, what you'll get is 2.5314. Okay, so now calculate your test statistic. That would be 3.25 divided by 2.5314, and that is 1.2839. Okay, so that's our test statistic. Next step in the testing procedure is to look at your test statistic and compare that to values on the t-table. Alright, so first, before we go to the t-table, we need to think of what is our degrees of freedom for our when we're looking at the t-table. So here, degrees of freedom is going to be nd minus 1, the number of differences minus 1. So that would be 7. So that would be 7. So now let's go and look at the table. So we have here the degrees of freedom. Our degrees of freedom is 7. So I'm going to zoom in and look at that one in particular. Okay. And remember our test statistic was 1.2 something. So we want to basically find two t-values. So inside the table, remember, is the t-values. We want to find like a sandwich for our t-values. Okay, so we'll right between these two values, 0.896 and 1.415. Our t-value, our observed test statistic, is between these two numbers. Okay, so then the corresponding p-value will be between 0.2 and 0.1. Now, do we need to multiply that by 2 or no? That depends on if our null hypothesis is two-sided or if our alternative hypothesis is two-sided or not. If it was two-sided, it would be something like mu not equal to 0. Or mu not equal to something. If it's one-sided, it's like greater than or less than or something along those lines. So in this case, we have a one-sided test because remember, we're trying to test if the depression score is higher in the active drug group than in the placebo group. So we have a one-sided test. So if we look up here, these numbers are corresponding to the one tail area. So we don't need to worry about multiplying our values by 2. We just know that our p-value is between these two numbers, and we leave it at that. So going back here, we know that our p-value is between 0.2 and 0.1. So the p-value, well, 0.2 is larger than 0.1, so I should write that on this side, and then I should write my p-value is somewhere between these two numbers. Okay, I think it's always a good habit to get into is drawing out your hypothesis just to make sure that you've done your p-value correctly. Okay, so remember we're trying to test. So here I'm going to draw this distribution here. Here is 0, and if the active drug is a higher number, right, than the placebo, then we would expect this difference to have been high. Remember, and that's what our alternative hypothesis, that's what our hypothesis testing is getting at. We want this difference to be high because we're testing if the active drug ratings or the scores are higher than during the placebo. Okay, so we're trying to test if our test statistic, our value for the test statistic, going to be in the high range. Okay, yeah, and that's what the these areas were corresponding to in our table. So that's just a double check to make sure that we've come up with our p-value correctly. So the last step in hypothesis testing is to make a conclusion. So what you do is you compare your p-value to some predetermined alpha level. So if the p-value is less than the alpha, then you reject the null hypothesis, and then if it's more than the alpha, then you're going to fail to reject. So usually alpha equals 0.05. In this question, it wasn't specified. So when it's not specified, just go ahead and assume alpha equal to 0.05. Okay, most in quizzes and exams and such, it will be specified alpha equals something. Okay, so here we'll assume alpha equals 0.05. So our p-value is greater than 0.05. So therefore, we fail to reject the null hypothesis. So our conclusion then would be we do not have evidence to support that the active drug helps, basically, that the active drug improves the depression rating.